All right, how's it going? So we just learned about powers and yeah, we learned about how to compute powers of complex numbers. Wasn't too bad. At least it's not as bad as I initially thought it was going to be. But now we have to learn how to do radicals of complex numbers. So that's doing things like square root 3 plus 4i, or the cube root, or the fourth root, or the fifth root. This process can get kind of long. For square roots, there is a bit of a shortcut. But for higher roots, there's no shortcut. It just happens to be a long process, as we'll see. Okay, so as usual, you should take notes as I'm writing, and then I'll do an example. You can do an example, and then we'll see how we're doing. So let me say now, intro sentence. We wish to learn how to compute radicals, sometimes called roots, right? Square roots, cube roots, fourth roots of complex numbers. And what they look like is it's like this: nth root of a plus bi, like that. We have some quick theory that we can go over. It's a bunch of paragraphs. I don't really want to write down all the paragraphs, so let's just go to the notes, advanced arithmetic, radicals. Oh my gosh. Scroll up and let's see what I have to say. And you can just write down stuff that I highlight. So some quick bullet points on theory. As it so happens, when you compute the radical or a root of a complex number, the amount of solutions you get is the same as the index n. And that index in green is right there. So if you're doing cube roots, you're going to have 3 answers. If you're doing fourth roots, you're going to have 4 answers. If you're doing 10th roots, God forbid, there will be 10 answers. If you're doing square roots, there's going to be 2 answers. Okay, so this happens to be a really, really famous result in mathematics, and they gave it a very special name, fundamental theorem of algebra. And in mathematics, whenever you hear the term fundamental theorem, it tells you that it's really important. That's the first bullet point. The second bullet point is a way to check our results. As it so happens, the n results will always add to give 0. So if you find the cube roots of a complex number, you're going to have 3 answers, right? If you add up those 3 answers, they had better give you 0, meaning everything should cancel out somehow. That will always happen. And there are some theoretical reasons for this. Pretty much, like I say it right here in blue, but visually, it's like your complex numbers will be evenly distributed around a circle, not the unit circle, but a circle. So maybe you'll have one that's like that, you'll have one that's like that, you'll have one that's like that. Let's call these complex numbers Z1, Z2, Z3. If you consider these as vectors and you add them vectorially, tip to tail, oops, Move that aside. And here's Z3. Of course, if you draw this accurately, you'll get a cycle. See how, oh my gosh. See how if you start at the red dot and go around, you just end up back right at the dot, right? So that means the vector sum is 0. That's the reason. It's not something we have to delve too deep into, but that's what it is. For us, it's a way to check our answers. So when you do a radical problem, computing the root of a complex number, you can check your answer by adding the results, and you better get 0. So there we go. Those are just some quick theory bullet points. Let's start with figuring out how to do square roots, because there is a bit of a shortcut method. And then we'll move on to cube roots and higher. So let's go back. And let's start with square roots. Oh. So there we go. And it's best illustrated with an example. So here's the example. And I'm just going to take this from my notes. Compute the square roots of, what do we got? 12i. So I'm going to show you this one. And then you can try another one. So first, oops. Let's write this down. Surely you would agree that the square root of negative 5 plus 12i, after you get the final result, it's going to look like a plus bi, right? In rectangular form. That's what it's going to look like. And so our goal is to figure out what a and b are. And to do that, this is what we call a radical equation, which is something here you would usually learn in high school, grade 11. And to solve it, we have to square both sides, essentially. So squaring both sides yields, what does it yield? Let's see. So I'm going to square both sides, and I'm going to get negative 5 plus 12i equals a plus bi squared, right? Because on the left side, if you square, then they're going to cancel out. And on the right side, I have a plus bi squared. And if you do the work and you FOIL it all out, you will get a squared. I can show my work once, just to show you how it would be. This is just scrap paper. If you had to do like this, you would FOIL a squared plus abi plus abi again plus b squared I squared. I squared is negative 1, right? So you would have this. And then these two blue guys are actually like terms. So double abi, and then we're going to have minus b squared. Oops, right? Because this I squared equals negative 1. So that's why there's a minus right there. And then as per usual, we like to write this as the real part plus the imaginary part I. So that's how I got that. You can choose to memorize it if you wish. It's up to you. But that's what we have so far. Okay, this red stuff. And right here, we have equality, right? This complex number equals this complex number. And you may recall, we learned what equality between complex numbers meant. It meant that the real part has to equal the real part, and the imaginary part has to equal the imaginary part. And so we can write all that down. So let me say now, equating the real equating the real and imaginary parts yields the system of equations a squared minus b squared should equal -5, and 2ab should equal 12. Right, so this yellow stuff had better equal this yellow stuff. That's this equation. And this blue stuff has to equal this blue stuff, not including the I. That's this blue equation. That's what we did. And in the second equation, I can divide by 2 just to simplify. So let me take this one and divide by 2. There we go. So that's what I have so far. I now have to figure out what a and b are. A times b has to be +6, and a squared minus b squared has to be -5. So there's a few ways to solve this system. You could do it the long way, which is using the high school method called substitution, which I don't want to go over, but I will show you in the notes where that is so you can learn it yourself. Not learn, but review it yourself if you wish. I claim that we will always be able to guess a solution to this. Just because these questions are hard enough as it is, usually they're set up so that you can just guess. Meaning they're going to have integer solutions. Now, the question is, how do we guess? What you do is you always look at this second equation to start. Two numbers that multiply to 6. Well, 1 and 6, 2 and 3, and in reverse as well, like 6 and 1 and 3 and 2. But really, it's just these two options. And then you think, this yellow stuff, 1 and 6, in this particular yellow combination, is it going to give me -5? And the answer is no way. 6 squared just by itself is 36. 1 squared is 1. No way a squared minus b squared is going to turn into this blue -5, right? No way. So this cannot be correct. So it must be the second case, 2 and 3. Well, 2 and 3 in some combination, not some combination, but specifically this yellow combination, result in -5? I think so, because if you do 2 squared minus 3 squared, that's 4 minus 9, and that does give you -5, so that's awesome. And just as a remark, if you needed to get +5, you would just do it the other way. You would do 3 squared minus 2 squared. If you wanted +5 specifically, but we want -5. So that means this has to be A, and that green guy has to be B. So that's how you guess. Of course, generally in mathematics, you won't always be able to guess, but we'll say for the purposes of our course, you will. And even if you can't, there is the substitution method as well. But in this case, we have AB could be, I think I said 2 and 3. Okay. Now, these aren't the only answers. It so happens that -2 and -3 also work, right? Is -2 squared minus -3 squared still equal to -5? You can verify, yes, it is. Is -2 times -3 still equal to the 6? Yeah, the negatives cancel out and 2 times 3 is 6. So that will always happen. Once you get one of the solutions, the other one will always be the negative or the negation. Okay. So we have A and B, but now finally we have to write down the answer. A lot of people forget and they'll stop here, but that's incorrect because that's not the final answer. You have to actually tell me what the square roots are. So now you would say thus. The square roots of, I think it was -5 plus 12i was the question, are simply so if you look way at the beginning, we said this square root was a plus bi, right? Way up here in yellow, that's what we said. And we have a and b. So in the first case, we have 2 plus 3i. And in the second case, we have -2 minus 3i. So there we go. These are the answers. These are the two square roots of the complex number -5 plus 12i. If you leave it like this, that's okay. It turns out you can simplify a little bit because from the second solution, you can factor a negative out and you'll have 2 plus 3i. And the first solution already is a 2 plus 3i like this with a plus in the front. Right? And then you can combine these two guys together and you can do plus minus, right? 2 plus 3i. And this is very comforting for us because when we take square roots, isn't there usually a plus minus in the front, right? So it's the same thing with complex numbers. There's going to be a plus minus when you're doing a square root. But there we go. This is the process of computing the square root of a complex number. Now, how much of this do we have to know? Usually, some people like to just memorize this yellow stuff right here, and they will memorize that a squared minus b squared is this blue guy up there, and 2 times ab is this green guy up there. So some people will memorize that, and they'll skip all of this beginning stuff, but some people will do all of it. You know, it's not a big deal. You can do whatever you wish as long as you get the correct answer in the end. Okay. Oh, all right. So that's that. Take a look. You all can try one as well. Maybe we'll try this one from the exercises in my notes. So why don't you try this one? Example Oh, compute the square roots of, oops, negative 11 minus 60i. So take a few minutes, try it out yourself, same methodology, write down the answers, and then unpause the video, and then you can compare your solution with my solution. Okay. Okay, let's see. So I am going to choose to just memorize this yellow result personally. So here's what I'm going to do. I'm going to say first denote the square root of negative 11 minus 60i as being a plus bi in the end, right? And so we have to solve the system. A squared minus b squared should be negative 11. And 2ab, don't forget the 2, should be negative 60. We don't need the I, like that. I can divide by 2. A squared minus b squared is negative 11. And a times b should be negative 30. And so we can guess. Maybe I'll just write it down here. Guess. Okay, let's see. Now, I need two numbers that multiply to negative 30. Okay. And in this fashion, a squared minus b squared give me negative 11. Okay. Well, two numbers that multiply negative 30, 1 and negative 30. Well, I don't really need the negative, but I will eventually, but not right now. 1 and 30, are these two numbers somehow going to satisfy this equation? No way, right? 30 squared is like 900. So there's no way a squared minus b squared is going to be 11. So that can't be it. 2 and 15. 15 squared is over 100, so no way, that's not it. 3 and 10? Ooh. No, 10 squared is 100. That's way too big. 5 and 6? This one looks promising. Let's try. A squared minus b squared is 5 squared minus 6 squared. What is that? 25 minus 36. Using a calculator, sure enough, is negative 11. So that means that this is my A and this is my B. A is 5 and B is 6. But here in yellow, they have to multiply to negative 30. So that means one of them has to be negative. So maybe I can make A be negative 5 and B be positive 6, like that. So there we go. That's my guessing. Let me erase all of this. And then remember, we said that the second answer is always the negative of the first. So 5 and negative 6. And you can verify both of these do indeed satisfy this system up here. So there we go. We were able to guess. And now we have to write down the answers. So I'll just say thus. Maybe I'll just say square root of negative 11 minus 60i equals negative 5 plus 6i, and 5 minus 6i. And you can leave your answer like this, or you can do the simplification. In this case, from the first one, I'm going to take a negative out, and the second one I'm going to leave as the same. 5 minus 6i. Oops. And sure enough, we do have plus and minus. 5 minus 6i. So there we go. Hopefully you also got the same answers, but that's how we do it. Nothing too crazy. Square roots are pretty good. But now when we get to higher roots, cube roots and fourth roots and fifth roots, those get pretty hard. So let's see how to do that next. Let me call the topic the subtopic. I don't know. Higher roots. Nth root of a plus bi. Box around this bad boy. Oh, right. Before that, sorry. Before that, I did say that yes, you can guess, but you could also do substitution. I don't want to show that right now live. I'll leave it to you to take a look. But if you go to my actual lecture notes, right, this is the radicals of complex numbers, and you scroll down a little bit, there is this screenshot right here. And this screenshot shows how we solved the system in the first example. Okay, we took this, in this case, we take the second equation and we isolate for b, and we sub that into this b right there. And then after some simplifying, you can get this yellow equation, which we were able to factor and figure out that a had to be plus or minus 2. And we also get that a could be plus or minus 3i from these green equations, but a has to be a real number. A can't be imaginary. So that's why this green stuff is extraneous. And then since we have a is plus minus 2, I can put that back into this blue equation up here to get b has to be plus or minus 3, right? 6 divided by 2 is 3. And that's another way you can solve these systems when you're doing square roots. I think it's better just to try and guess. But if you want to do it this way, some people like doing it this way, so that's totally fine. It's not a big deal. Okay. So let's go back. And see how we can do higher roots of complex numbers. As I said, it's not the easiest thing to do. And I do have steps for it. I'm looking at my notes right now. I'll see if I can write the steps down in shorthand. But you can look at the notes to see the steps. Here are the steps, we'll just say. First, we convert to polar form. Convert a plus bi to to polar form. And then we write this down. We denote that the nth root of whatever this polar form is from step 1 we know ultimately it's going to look like r angle theta. For sure, right? Like when you do the nth root, the result ultimately is going to look like this, right? And then what we do is we can take this equation and you can rearrange, not rearrange, but you can move the radical to the right-hand side. So you would have something that looks like this. Instead of an nth root, you would now have an nth exponent. And this looks exactly like de Moivre's theorem, right? So this is going to be r to the n angle n times theta. That's what we're going to have. So that's step 2, is to do all of this. And again, this is that so-called de Moivre's theorem, which is like r angle theta to the n is r to the n times theta. We learned this in the last section when we did powers of complex numbers. Okay. So that's step 2. And then step 3 is to find the r and the theta values, right? Because remember, we're trying to find this yellow stuff, right? That's the goal. So we got to figure out r and theta next. So maybe I'll say, maybe I'll just write down find r and theta. I'll just write that down, and then we'll see the example, what it looks like. And then number 4 is finally write all your answers down. Remember that if you're doing 4th roots, you're going to have 4 answers. If you're doing cube roots, you're going to have 3 answers. You write the answers down and convert to rectangular. So that's how we do it. Those are the steps. Not as nice as I would like to have written them down, but that's okay. Let's see an example. So I'm just going to take it from my notes because this stuff is now getting too hard to make up examples off the top of your head. Determine the cube roots. Determine the cube roots of the complex number negative 27i. So the real part is 0. A equals 0, B equals negative 27. So this is going to be a long one. Here's how we do it. First, we convert to polar form. And we know how to do that. Draw the picture. And negative 27 is straight down like that. There's my r. That's my theta. This is negative 27 down there. Now, sometimes your complex number is this special case where it's like It's either straight to the right or straight up or straight to the left or straight down. In these cases, you don't have to do all that work to find r and theta. We can clearly see what r and theta have to be from this picture. Right? Because r is just the length of that blue vector. That's 27, right? r equals 27. And theta is that blue angle that has to be 270 degrees. So in this case, we don't have to do all that math. You can do it visually. But of course, if you had a complex number that was like over here somewhere like that, then you do have to draw the triangle, find r, find theta. In this case, we don't. So we figured out that negative 27i in polar form looks like this. So step 1 is done. And then scrolling up, step 2 is this guy. We write the nth root of the polar form as this yellow stuff and then apply de Moivre's theorem. Oops. So let me do that right now. So next we denote, and we're doing cube roots, right? Yeah, we're doing cube roots. So I'm going to denote the cube root of this polar number that we just found. And once you do the cube roots, we are expecting it'll look like r angle theta, right? And our goal is to figure out what r is and what theta is. And to do that, we can rewrite it by moving the radical 3, sorry, the index of 3 to the other side. So it'll be r angle theta cubed, and then we can do de Moivre's theorem, right? R cubed angle 3 times theta. So that was de Moivre's theorem. And so now what we have is we have this polar number equal to this polar number. And so two polar numbers are equal if the modulus equal the modulus in blue and the angle equals the angle in yellow. So that gives us two equations. Let's write those down. Now we get the two equations. R cubed equals 27, and the angle 3 theta has to equal 270 degrees. And again, this blue equation is from those two guys being made equal, and this yellow equation is these yellow guys being equal. Now, the only thing is we have to consider coterminal angles now. So 270 is not good enough. You have to consider 270 plus 360 is 630 degrees. And then plus 360 again is 990 degrees. So we have to do that. And the reason we have to do that is because since we're doing a cube root, we expect 3 answers, right? And each of those 3 answers are going to be off by, it's actually not by 360, it's actually going to be 360 divided by 3, which is 120. They're off by 120. And because you need 3 of them, we have to find 2 coterminal angles so that in total, we have 3 angles, right? 1, 2, 3. That's what you need to do. If this was a 4th root, you would have to find a 4th coterminal angle as well. If it was a 5th root, you'd have to find another one so that you can have 5 angles in total. And let me write that down just so we have a sentence in our notes. So maybe I'll say, how should I phrase it? Maybe I'll say must find. Yeah, that's okay. Must find enough coterminal angles so that the total amount of angles that we have equals the index. And in this case, because we're trying to find cube roots, the index is 3. So we need 3 angles in total. And we have them, okay? Hopefully that makes sense. And now we can solve for r and theta, right? So first equation, r cubed is 27. So that means r equals 3. And the second equation, I can divide by this yellow 3 to get theta by itself. So theta equals 270 divided by 3 is 90. 630 divided by 3 is 210. 990 divided by 3 is 330 degrees. So there we go. That was step 3. Step 3 is get r and theta. That's all of this stuff on the screen. This is step 3. Finally, we write down the answers. And the answers are all going to have this yellow structure. R angle theta, here's my r, and here are 3 thetas. So we're going to have 3 answers. So I will just say thus. Oops. Cube roots of, I think it was negative 27i, are not so simply, because this is going to take a while. Let's call the answers z subscript 1, z subscript 2, and z subscript 3. Why are we using the variable z? It just so happens in complex numbers, when we're giving variables to complex numbers, we use z. That's just how it is. So r angle theta, r angle 210 from way up there in the top right, r angle 330 degrees. Technically, these are the answers, but we have to convert them to rectangular form. And we know how to do that, right? We use cosine sign. 3 times cos 90 plus I times sine 90 cos 210. Man, I'm starving. Holy shit. Maybe I should order some McDonald's or something. I've been cooking at home all day long for weeks now, and it's getting boring. Maybe Wendy's. Wendy's is a bit better, I think. But frick, man, freaking Skip the Dishes. They upsell all their prices. It's so annoying. I mean, I can understand, right? They have to make money, but holy shit, fucking $6 burger all of a sudden costs $9. Are you serious? Get out of here. So you have to know your unit circle. Cos of 90 is 0. Sine of 90 is 1. Well, I don't want to say know your unit circle. You have to know how to do all of these guys. Okay. If you don't remember how to do that, you can go back and look at our trigonometry notes. And the topic in my notes would be exact values of trig ratios. That's what I called it. What is cos of 210? I don't even know. 30 cosine 60, negative root 3 over 2. Sine of 210 is a half. Oh, sorry, negative a half, I think, actually. Negative a half. 3 times. That's going to be root 3 over 2. And I think that is still negative a half. So there we go. And then you would multiply the 3 inside, right? For all of them. And finally, we get our answers 3i minus half I minus half I again. So there we go. Finally, these answers are the 3 cube roots of negative 27i. And it took all of this work to do. There you go. There's the full example. That's just how it is. You want to skip steps? Please do. Easy for me to mark. We can skip steps, totally fine. But just to recap, in green, all of this was step 1, convert to polar. And then step 2 was, what did I say step 2 was? Where is it? Oh, right there. Here are the steps. Oh yeah, do that polar form de Moivre theorem stuff. So step 2 is all of this. And then step 3 is get the r and the theta. Be mindful of this yellow comment. We need to get coterminal angles. And then step 4, which ironically is the last step, the hardest step, I mean, is do all of this computation to get the answers. Okay, that's just what it takes. Not a big deal. Sometimes math is hard. And we can check our answer, right? So you may remember a few minutes ago, I don't know, I think this took 20 minutes actually, I said that if you take these yellow guys and you add them up, you better get 0. They should all cancel out somehow. And I guess I can show you this one time. So I'm going to do check. Let me take Z1 plus Z2 plus Z3 and see what happens. So Z1 is 3i, Z2 is minus 3 root 3 over 2, minus 3 over 2i. Oh, I'm missing 3's. So right there and there, those ones should be threes, right? My bad. 3, 3. Then plus Z3 is that. So these blue guys somehow are going to add to 0. Well, sure enough, this cancels that, right? And all we're left with is this red guy, and this red guy. They're all imaginary numbers, so they all have an I on them. Let me factor the I out as a common factor. So then I'll have 3 minus 3 over 2 minus 3 over 2. You can use a calculator if you want. That's going to turn into 0. So sure enough, we are happy campers because we got the right answer. So that's how you check. So I don't know how long it's been, but we'll give you this one question to try just from my lecture notes. Let me line everything up again. Very nice, very neat. Example. So I want you all to I want you all to try the fourth roots. Determine the fourth roots of, from my notes, -8 plus 8 root 3i. So there we go. Try this one out. It's going to be exactly the same process. Step 1, convert to polar. Step 2, do that denote the fourth root as r angle theta and then apply de Moivre's theorem stuff. Step 3 is find the r and theta. And for the theta, you have to consider coterminal angles, right? In this case, because we're doing the fourth roots, we better have 4 angles. And then step 4 is write all the answers down. So pause the video, try it out. Honestly, this might take you even like 15, 20 minutes just to do this question. And that's okay, because it's the first time we're learning it, right? It's going to take a while. And then when you're ready, you can unpause and check out my solution. Okay. Okay, let's see. Oh my God. You guys ever play that game Jackbox? I think they're on version 7 now. I don't know. Jackbox. I think there's 7 of them. That's what I'm going to do after this. Maybe order some Wendy's, play some Jackbox with some friends, and then life is good. So let's see. Determine the fourth roots of this number. First, convert to polar form. I think this guy is in quadrant 2, so bada bing, bada boom. Imaginary axis, real axis down there. We've done this many times now. In this case, no shortcuts. We just have to do it. R is a squared plus b squared. You can chuck this in the calculator if you wish. Be very mindful of how you use your brackets. I think that's 64, 16. Is that 16? I think it's 16. Theta equals 180 minus the reference angle, which is tan inverse B over A. So 180 degrees minus tan inverse opposite over adjacent. The absolute values, just get rid of the negative sign, this negative. 8s cancel out. Tan inverse of root 3 happens to be 60 degrees. You can use a calculator for that. It'll give it to you exactly. Just because root 3 is a number on the unit circle. That's the reason why it gives it to you exact. So 120. Step 1 done. But let's write down the result. So we have that our complex number is the same thing as R angle 120 degrees. That's step 1. And then step 2 is to do that de Moivre theorem stuff. So I'll just say next. We denote the fourth root in this case, right? 16 angle 120 degrees is ultimately going to look like R angle theta. I can move the index of 4 to the other side of the equation as an exponent. To the power 4 this time, not the index of 4. And using de Moivre's theorem, I get that. That's what I got. And now I can equate, right? So I can equate the modulus. R to the 4 should be 16. And I can equate the angles. 4 theta should be 120 degrees. So again, this yellow stuff are these guys together. And this blue stuff are these two guys together. Oh. And I need coterminal angles. Because I'm doing a fourth root, I need 4 angles in total. I already have 1, which means I need to find 3 coterminals. So 120 plus 360 plus 360 is 480 degrees. Plus 360 again is 840 degrees. Plus 360 one more time is 1200 degrees. Okay, so that's just me adding 360, adding 360, adding 360. And now I have 4 angles. So I can solve for R and theta. R to the 4 equals 16. So R is to be 2, right? Because 2 to the 4 is 16. And theta divided by 4. So 120 divided by 4 is 30. 480 divided by 4 is 120. And then 210. And then 1200 divided by 4 is 300. So there we go. There's my R and theta. And then that's step 3, all done. Step 4 is write the answers down. And the answers are all going to have this yellow structure. And I have r and theta right here. So I'm going to have 4 answers. 1 answer for each angle. So I'm going to say thus, the fourth roots of, what was the question? -8 plus 8 root 3i are, so we'll denote them as Z1, Z2, Z3, and Z4. R was 2, so R angle theta, R angle 120, 2 angle 210, 2 angle 300. So again, these are the answers in polar form, but we want them in rectangular form. So we got to use cosine sine. So there's that one. But yeah, anyways. So Wendy's, I think I'm gonna get my usual Dave's single cheese. I think that's what it's called. I don't know. And then we'll get some large fries. Oh, whoops. And then maybe for the drink, get some chocolate milk. Maybe that's the game plan. I don't know. You know what's really dumb though? If you go to Wendy's and you large size something and you order chocolate milk, they still only give you 1 carton of chocolate milk. The tiny ones, the 250 milliliter ones. You'd think they would give you 2 if you large size it, but no, they only give you 1. So that's kind of dumb. But anyway, so you have to use your trig knowledge to figure out all of this stuff. What is this? Cos 30 sine 60, root 3 over 2. Sine of 30 is a half. Cos 6, negative a half. Negative 3 over 2. Half. So I believe this is what you should have gotten. And then how nice, we can multiply the 2 inside for everything, and all of the fractions cancel out. So root 3 plus I, negative 1 plus root 3i, negative root 3 minus I, and 1 minus root 3i. There we go. These are the 4 fourth roots of this complex number, those guys. And there's 4 of them, like we expect. And if you add them all up, everything will cancel out and you get 0. So that's good. But yeah, so here's the example on the screen if you want to, I don't know, take a screenshot or whatever. You should have been writing this down, but up to you. So that's how we do it. Again, step 1 was convert to polar. Step 2 was to do this stuff. Step 3 was solve for r and theta. And then step 4 is get the answers. So that's how we do it. That's how you find radicals of complex numbers. If you had to do a 5th root, that just makes it even longer. If you had to do a 6th root, that makes it longer. But the process is still the same. And there we go. That's how we do radicals. 4th root, cube root, and then square roots. Okay. So that's all I have to say about that. I guess this is my second YouTube video, so perhaps I will end it by saying like and subscribe, comment down below, but don't comment any math questions. I don't want to answer any math questions. No, I'm just kidding. You can comment whatever. You should comment what your Wendy's order is going to be. That's what you should do. Okay. Hopefully this made sense. You can message on Teams if you have questions. I'm going to get going. So it was nice seeing everybody. So I'll see you next time. What the? Still not used to stopping the recording. All right. See you later.